Examples of equal sets. So we've started a new section now, and this section is all about putting what we've discussed, the idea of equal sets, into practice. We're going to look at several examples to really solidify your understanding. As a quick reminder, and this is really important, two sets are considered equal if and only if they contain exactly the same elements. Now, pay close attention to this next part. The order in which you list those elements doesn't matter at all. We'll see this play out in the examples. So, if two sets have the same members, just arranged differently, they are still considered equal. We'll be exploring this concept in detail through the examples on the following slides, so keep this in mind as we go through them. We'll also be looking at a slightly trickier case with repeated elements later on, so it's good to have this core principle firmly in your mind right now. Understanding the core principle. The first point here states that the fundamental idea behind equal sets is that the contents of the sets must be identical. What this means is, if you were to list out all the things inside one set, and then list out all the things inside another set, those two lists have to have exactly the same items for the sets to be considered equal. Next, it says the arrangement of the elements within the set does not affect whether two sets are equal. Remember, in example 1, we had a set with 1, 2, and 3, and another with 3, 2, and 1. This point reinforces that the order doesn't matter at all. A set is defined by what it contains, not the order in which you write those things down. Finally, it emphasizes that we are only concerned with what is in the set, not how it's written. This is a crucial point to remember. Think of it like a recipe. If two recipes call for the same ingredients, they're essentially the same recipe, even if the instructions are worded slightly differently. So let's move on to slide 2. As we discussed on the previous slide, we're learning about equal sets. Now, this slide really gets to the heart of what makes two sets equal. Keep this in mind as we move forward to more examples, because we'll be seeing this principle applied again and again. We'll soon look at an example where the order is different, and then we'll tackle a slightly trickier case involving repeated elements, so pay close attention to this core concept. Example 1. Simple numerical sets. Let's move on to our first example of determining if sets are equal. As we discussed on the previous slides, remember that the core idea is to check if the contents of the sets are identical and the order doesn't matter. So on this slide, we have two sets defined for us. Set A is represented as 1, 2, 3, and set B is represented as 3, 2, 1. Now let's read that out carefully. Set A contains the numbers 1, 2, and 3. Set B also contains the numbers 1, 2, and 3. The question we need to answer is, are these sets equal? To figure that out, let's check the elements. If we carefully look at both sets, we can see that both sets contain the numbers 1, 2, and 3. Now here's the important part. Order doesn't matter. Notice that the elements are listed in a different sequence in each set. In set A, we have 1, 2, 3, while in set B, it's 3, 2, 1. But because they both contain exactly the same numbers, this difference in order doesn't affect their equality. Therefore, we can conclude that it is equal to be both sets are equal because they have the exact same elements, regardless of how they are arranged. Keep this in mind as we move forward, because we'll soon see an example where the order does make a difference. Specifically, when the number of times an element appears within a set is different, as we'll explore on the next slide. Example 2. Sets with different presentation. So let's move on to another example to really solidify this idea of equal sets. On this slide, we have two sets defined as follows. Set C contains the elements A, B, and C, and we write that as C equals the set containing A, B, and C. Set D is defined as containing C, A, and B. Now, just like we did with the previous example, we need to determine if these two sets, C and D, are equal. Remember, the key is to focus on what elements are in each set and not how they are arranged. Let's identify the elements. If we carefully look at both sets, we can see that both set C and set D contain the letters B and C. And this is crucial. The order in which these letters are listed is different. In C it's a B, C, and in D it's C, a B, but that doesn't matter. We ignore the order when checking for equality. The sets have the same members. Therefore, we can confidently say that C is equal to D. Both sets are equal because they have exactly the same elements, regardless of the order in which those elements are presented. Keep this in mind as we move forward, because we'll soon look at a slightly trickier example involving repeated elements, where the number of times an element appears becomes important. But for now, you should be comfortable recognizing that different orderings don't change the equality of sets. Example 3. Sets with repeated elements, important note. Let's move on to our third example, and this one is really important because it highlights a common misunderstanding about sets. We're going to look at two sets, set E and set F. Set E is defined as 1, 2, 2, 3. And set F is defined as 1, 2, 3. Now the question is, are these sets equal? Take a moment to think about what we've discussed on the previous slides. Remember, for two sets to be equal, they need to have exactly the same elements. Let's break it down. When we look at the elements and their count, we see that set E contains the number 2 twice, while set F contains the number 2 only once. This is where a key principle comes into play. Equality between sets requires not only that the elements are the same, but also that the number of times each element appears is identical. Because the count of the element, 2, differs between the two sets, they are not equal. Therefore, we can say that E is not equal to F, written as E not equal to F, and this brings up a crucial point about how we represent sets. Sets, by definition, only list unique elements. So, while we might initially write a set as 1, 2, 2, 3, the correct and standard way to represent it is simply 1, 2, 3. We don't repeat elements within a set. Keep this in mind as we move forward because it's a fundamental concept in set theory. Example 4. Sets with different representations of the same element. Let's move on to our fourth example. On this slide, we have two sets, G and H. Set G is defined as containing the numbers 1, 2, and 3. We represent this mathematically as G equals the set containing 1, 2, and 3. Set H is defined as containing the numbers 3, 1, and 2. So, H equals the set containing 3, 1, and 2. Now the question is, are these sets equal? It's a good check for your understanding, especially after looking at the previous examples. Let's check the elements. If you look closely, both sets contain the same numbers, 1, 2, and 3. And remember what we discussed earlier, the order in which we list the elements doesn't matter when determining if two sets are equal. The elements themselves are the same, we've just written them in a different sequence. Therefore, we can confidently say that G is equal to H. Both sets are equal because they have exactly the same elements, regardless of the order they're presented in. This reinforces the core principle we've been building on. Equality of sets depends solely on their contents, not their arrangement. Keep this in mind as we move forward and remember the important distinction about repeated elements, which we covered in a previous example. Key takeaways. Let's recap what we've learned about equal sets with these key takeaways. First, and this is really important, two sets are equal if and only if they contain precisely the same elements. What that means is, equality isn't just a similarity, it's a perfect match. Every element in one set must be found in the other, and vice versa. There can't be any extras or missing pieces. Next, remember that the order in which the elements are listed within a set is completely irrelevant when determining equality. We saw this in examples 1 and 2, where we had sets like 1, 2, 3, and 3, 2, 1. Even though the order was different, they were still considered equal because they contained the exact same numbers. Don't let a different arrangement trick you. Finally, and this is where students often make a mistake, the number of times each element appears in the set is crucial. If the counts differ, the sets are not equal. Think back to example 3, where we had a set with 1, 2, 2, 3, and another with 1, 2, 3. Because the number 2 appeared twice in the first set but only once in the second, they weren't equal. Sets, by definition, only list unique elements. So, while you might write 1, 2, 2, 3, it's mathematically the same as 1, 2, 3. Keep these 3 points in mind, and you'll be able to confidently determine whether two sets are equal. Now, on the next slide, we'll discuss some common mistakes students make when working with equal sets, so we can avoid those pitfalls. Common mistakes. A common mistake is to assume that two sets are not equal simply because the elements are listed in a different order. Now, remember back to examples 1 and 2, where we had sets like A equals 1, 2, 3, and B equals 3, 2, 1. We established that the order doesn't matter. So, don't let a different arrangement trick you into thinking the sets aren't the same. Always remember to focus on the contents of the sets, not the arrangement. This is the key takeaway here. When you're comparing sets for equality, mentally ignore how the elements are written down and just check what elements are present. Another mistake is to overlook repeated elements. Sets only contain unique elements, so the number of times an element appears matters. This builds on example 3, where we had E equals 1, 2, 2, 3, and F equals 1, 2, 3. We saw that because 2 appeared twice in set E but only once in set F, the sets weren't equal. Sets, by definition, don't allow duplicates. So, when checking for equality, make sure each element appears the same number of times in both sets. Let's move on to this final slide, which highlights some common pitfalls students often encounter when working with equal sets. This is really important to nail down, so pay close attention. Essentially, this slide is a reminder to be thorough and precise. Don't be fooled by appearances, focus on the actual elements and their counts. And with that, we've covered the basics of equal sets. Are there any questions about these common mistakes or anything else we've discussed?